Chapter 1 laid a foundation of the general characteristics of functions, equations, and graphs. In this chapter and the next two, we'll explore the theory and applications of specific families of functions. We begin this exploration by studying three interrelated families of functions: polynomial, power, and rational functions. These three families of functions are used in the social, behavioral, and natural sciences. This chapter includes a thorough study of the theory of polynomial equations. We investigate algebraic methods for finding both real and complex number solutions of such equations and relate these methods to the graphical behavior of polynomial and rational functions. The chapter closes by extending these methods to inequalities in one variable. Now, in 2.1, we're going to talk about linear and quadratic functions and add that to modeling. Now, polynomial functions are among the most familiar of all functions. You've been working with these since your days in algebra. Now, the definition of polynomial function goes like this. Let n be a non-negative integer, meaning it's got to be 0 or positive, and let a sub 0, a sub 1, a sub 2, all the way to a sub n be real numbers where a sub n cannot be 0. The function given by f of x equals a sub n x to the n power plus a sub n minus 1 times x to the n minus 1 power, all the way plus a sub 2 x squared plus a sub 1 x to the first plus a sub 0 is a polynomial function of degree n. The leading coefficient is a sub n. Now, I realize it was all a bunch of gibberish there, but the most important thing that we'll see is all of our powers, in order to be a polynomial function, the power has to be positive or 0. It cannot be negative. If the power is negative, it will not be a polynomial function. Now, the 0 function, f of x equals 0, is also a polynomial function. It has no degree and no leading coefficient. Now, polynomial functions are defined and continuous on all real numbers. That's the big idea here. They are continuous, which means you do not have to lift your pencil. Now, it's important to recognize whether a function is a polynomial function or not. So that's what we're going to do in example 1. Now, which of the following are polynomial functions? For those that are, state the degree and leading coefficient. For those that aren't, explain why not. So if we look at A, well, all the powers are either 0 or positive. So yes, this is a polynomial function. The degree is going to be the highest number that is an exponent. So my degree is 3. The leading coefficient is the number in front of that x term, so that will be 4. Now, if you look at B, is this a polynomial function? Well, the power here is -4, so this is not a polynomial function because of the -4 as a power or as an exponent. Now, if we look at C, what we'll have, this will really be 9x to the 4th plus 16x squared to the 1/2 power. This will not simplify. 9x to the 4th plus 16x squared will not simplify. So this is not a polynomial function. The square root, or the radicand, the stuff under the square root, it will not simplify. Now, if you look at D, Our powers here are x to the first and x to the fourth. There is my degree term, highest degree term. So this is yes. This is a polynomial function. My degree will be 4. And my leading coefficient will be -2. Because that is the number in front of your x to the fourth. Now I realize that x to the fourth is not the first term in that polynomial, but it is the highest degree term. That's why the degree of this polynomial is 4. Now the zero function, all constant functions are polynomial functions. Some other familiar functions are also polynomial functions as shown below. The zero function, which is the form f of x equals 0, is an undefined degree. The constant function, where f of x equals a, is really 0 degree because that's like ax to the 0 power. The linear function, f of x equals ax plus b, will be to the first degree because there's the power really on the ax. That's really ax to the first power. A quadratic function is ax squared plus bx to the first plus c, so that tells you it's of degree 2. Now, linear equations and graphs of lines were reviewed in sections P3 and P4, which we didn't go over, but the material is in there. And also we talked about some examples in Chapter 1 that also involve linear functions. We now take a closer look at the properties of linear functions. Now, a linear function is a polynomial function of degree 1, and so is a form ax plus b, where a and b are constants and a can't equal 0. Now, if we use m for the leading coefficient instead of a, and let y equal f of x, then this equation becomes the slope-intercept form of the line, or y equals mx plus b. Now, vertical lines are not graphs of functions because they fail the vertical line test, and horizontal line tests are graphs of constant functions, or degree 0. A line in a Cartesian plane is the graph of a linear function if and only if it is a slant line, which means neither horizontal nor vertical. Now we're going to apply some formulas here from P4, which is talk about slope, and also point slope form or slope-intercept form of the line. This should be fairly simple for you. You've been doing it since algebra. Now, this may be different terminology, different forms here, but really, there's x, there's y, so x1 and y1, here's x2 and y2. So in order to find slope, remember, it's y2 minus y1 over x2 minus x1. So when we do this, we'll have -2 minus 2 over 3 minus a -1, which will be -4 divided by 4, or -1. So there's your slope. Now, we can do this a couple different ways. We can use the point slope form of the line, or we can use y equals mx plus b. I choose to use y equals mx plus b here. So what we can do is, if we're going to use y equals mx plus b, you want to choose one of these 2 points. I'm going to choose the one on the left here, -1, 2. So what we can do here is then 2 will equal -1 times -1, because that's x, plus b, which means 2 will equal 1 plus b, which means b will equal 1, which means your equation, y equals -x plus 1. What that will be a slanted line, as you can see here. There's your graph of y equals mx plus b, or -x plus 1. Moving on to b, what we'll have, we have the points -5, -1, and 2, 4. So really, my slope will be 4 minus a -1 over 2 minus a -5, which will simplify to 5 over 7. Now I'm going to choose one of the 2 points. Let's choose actually a positive one so we can make it nice, easy, and positive. That's what we'll have. Simplifying, we'll have 4 equals 10/7 plus b. Now we're going to subtract that, which means b will be 4 minus 10/7. What's nice, that's why we have our calculator here. 4 minus 10/7 would be 18/7. And leave it just like that, that's fine. Which means your equation will be y equals 5/7 plus 18/7. Now if you're going to put that in your calculator, we could do 5/7, so put 5/7 in parentheses, x, plus 18/7, and you graph that. So there's your line right there. Now, one thing I do want to show you, though, to show you that these points are actually on this line, second trace and value. If I put -5 in, you will get -1 there as that's on the line, and then you put 2 in, you also get that point is also on the line. Now, another property to characterize a linear function is its rate of change. The average rate of change of a function y equals f of x between x equals a, where a does not equal b, is f of b minus f of a over b minus a. So really what that is, that's talking y2 minus y1 over x2 minus x1. Now, the constant rate of change theorem. A function defined on all real numbers is a linear function if and only if it has a constant non-zero average rate of change between any 2 points on this graph. We'll get into this. Now, because the average rate of change of a linear function is constant, it is simply called the rate of change of the linear function. The slope, which is m, is the rate of change of a linear function. In exploration 1, we're going to revisit example 7 of section P4 in the light of the rate of change concept. Now, you guys actually didn't do example 7, but we'll work on this exploration now. Now, Camelot Apartments bought a $50,000 building for tax purposes and are depreciating it $2,000 per year over a 25-year period using straight line depreciation. What is the rate of change of the value of the building? Well, if it's depreciating $2,000 a year, that means it's going to be negative $2,000. So there is a rate of change. Now we need to write an equation for the value v of t of the building as a linear function of time since it was placed in service. So that means v of t will equal negative 2,000 t plus 50,000. $50,000 is our y-intercept. That's where we bought the building. Now, if we want to, what I want to do then, let's actually plug that into our calculator. And we're going to change our window a little bit. So we'll go 0 to, let's say, 30 years. Then we'll go 0 to 60,000. So that's what it's going to look like. Now we want to find v of 0. Well, v of 0 should be fairly simple. That's what we bought it at. Negative 2,000 times 0 is 0, plus 50,000 will be 50,000. V of 16, it'll be negative 2,000 times 16 plus 50,000. That will give us 18,000. What that's doing, that's giving us the value of our building after 16 years, after depreciating it $2,000 every year. Now the next thing we need to do, we need to figure out when the building's going to be 39,000. So it's going to be 39,000 is equal to negative 2,000 t plus 50,000. We're going to subtract 50,000 from both sides. So you get negative 11,000 equals a negative 2,000 t, which means t will be 5.5 years. So the building will be worth $39,000 after 5.5 years. So again, I'm going to put in here 39,000. And we're going to find the intersection. And you can see there, x will be 5.5, which is really just like a t. Now to change things up a little bit, I'm going to talk about the question at this time to see if people are paying attention. So what I want you to do is send me a personal message to Mr. Gervis Classes on Facebook and give me the name of the daredevil who jumped from a space capsule this past weekend, and what height did he jump from in miles. So again, the name of the daredevil and what height he jumped from in miles from the space capsule. Now the rate of change of a linear function is the signed ratio of the corresponding lines rise over run. That is, for a linear function y equals mx plus b, the rate of change is m, or rise over run, or the change in y over the change in x, which is delta y over delta x. Now you'll see a lot of those deltas once you move on to calculus. Now this formula allows us to interpret the slope or rate of change of a linear function numerically. For instance, in exploration 1, the value of the apartment building fell from $50,000 to $0 over a 25-year period. In table 2.1, we're going to commute change in y over change in x. It's a non-zero constant, 2,000. The building's value is a linear function decreasing at a rate of $2,000 per year. So, here's what we're going to have. The y value is what we need to figure out, and the change in years. So that the y value after 1 year was 48,000. After 2 years was 46,000. 3 years was 44,000. And 4 years was 42,000. Now the change in x from 0 to 1, change in x will be 1. Change in x from year 1 to year 2 is 1. So those all be 1s there. And also the change in y, this will be negative 2,000. It all went down $2,000 every year. So that means your change in y over the change in x will be negative 2,000. Because negative 2,000 divided by 1 is negative 2,000. So that's how you can see it numerically. Now, in exploration 1, as in other applications of linear functions, the constant term represents the value of the function for an input of 0. In general, for any function, f of 0 is the initial value of f. So for a linear function, f of x equals mx plus b, the constant term b is the initial value, or the y-intercept, of the function. For any polynomial function, the constant term f of 0 equals a sub 0 is the function's initial value. So you can find the initial value of any function that you have by putting 0 into the function and just looking at the last term of the polynomial if it's a constant. Finally, the initial value of any function, polynomial or otherwise, is going to be the y-intercept of your graph. So it's going to be nice if you need to graph these by hand. You can always find the y-intercept of the graph by putting 0 in for x. Now we can summarize what we've learned about linear functions. The point of view, so if we think about a verbal point of view, a line is a polynomial of degree 1. Algebraic point of view, f of x equals mx plus b. Graphical, that's just a slant line with slope m and y-intercept b. And then analytical, a function with constant non-zero rate of change. It's increasing if the slope is positive, it's decreasing if the slope is negative, and the initial value is always when x is equal to 0. So in this book, we're always going to use 4 different points of view about any different type of function: verbal, algebraic, graphical, and analytical. Now, in section 1.7, we approach modeling from several points of view. Along the way, we learn how to use a grapher to create a scatter plot, compute a regression line for a data set, and overlay a regression line on the scatter plot. We touched on the notion of correlation coefficient. We're not going to go deeper into those ideas. Now, figure 2.2 shows 5 types of scatter plots. And you'll see these here. When the points of the scatter plot are clustered along the line, we say there's a linear correlation between the quantities represented by the data. When an oval is drawn around the points in the scatter plot, generally speaking, the narrower the oval, the stronger the linear correlation. So if we look here, we have a strong linear correlation, positive linear correlation here. In the next one in the middle, it's a weak positive linear correlation. In the C graph, there's little correlation. In D, there's a strong negative correlation. In E, there's a weak negative linear correlation. So if we talk about these linear correlation coefficients, the correlation coefficient is always going to be between -1 and 1. When R is greater than 0, it's a positive linear correlation. When R is less than 0, there's a negative linear correlation. When the absolute value of that R value is 1, or about 1, there's a strong linear correlation. When it's about 0, there's weak or no linear correlation. Now, we've already kind of talked about this, but it's good to talk about it again and get a better understanding of it. Now, correlation informs the modeling process by giving us a measure of a goodness of fit. Good modeling practice, however, demands that we have a theoretical reason for selecting a model. In business, for example, fixed cost is modeled by a constant function. Otherwise, the cost would not be fixed. Also, if you think back to the homework in section 1.7, we had to figure out which type of regression would work for a certain data set. We'll get into that a little bit more as we move along. Now, in economics, a linear model is often used for the demand of a product as a function of its price. For instance, suppose Twin Pixie, a large supermarket chain, conducts a market analysis on its store brand of donut-shaped oat breakfast cereal, Cheerios, but it's a store brand. The chain sets various prices for its 15-ounce box at its different stores over a period of time. Then, using this data, the Twin Pixie researchers project the weekly sales of the entire chain of stores for each price and obtain the data shown. So here's our data. Now, we need to use that data in table 2.2 to write a linear model for demand as a function of the price. So, in your calculator, we need to set up a scatter plot. So press Stat and enter on edit. In list 1, you're going to put $2.40. Put all the costs into your calculator. I want you to take a minute to do that right now. Now again, remember, your lists need to be the same length. Now I want you to put this in your calculator to get practice. So you don't come up to me later in the year saying, I don't know how to do linear regression, Mr. Garber. Well, this is how you do a linear regression. Now a good window here, the window that we want to use will probably be, I would think, we can make our X-min 2, our X-max 4, because that's $2 to $4. We can make that 0.2 for our scale. Then, what I want to use here, I want to use 10,000 to 40,000. And we can make this 10,000 for the Y scale. Take a minute to switch your Y scale, or add your window. Once we do that, we want to press second Y equals. We're going to turn on plot 1. Then we can graph it. What type of linear correlation does this do? Well, it almost looks like it's a strong negative correlation because it looks like a line going down. Now, in order to find a linear model, what we want to do, we're talking cost here, so change your float in this case to 2, so press the mode button, go to 2 and press enter. What we want to do, press stat, scroll right to calculate, and down to 4, which says linear regression. We want to put list 1 in, so second 1. The comma, which is underneath the sign button. Second 2, which is list 2, comma. Now, in order to put this automatically into our calculator, we want to press the bars button, which is next to clear. Go over to Y bars, press enter on function, enter on Y1. Now, this will automatically put our equation into Y1, press enter, and we have this as an answer. Now, if you notice, I don't have a diagnostic on. So what I want to do, I'm going to go put my diagnostic on. I'm going to press second enter a couple times to get this back up. Now when I do that, I have a diagnostic on. Now you can see that the R value is negative 0.98, which means it'll tell you it's a strong negative correlation. So our equation will be Y equals negative 15,358.93x plus 73,622.50. So there's our regression equation. Now what we want to do, when you graph that, that's what it's going to look like. So that's what your equation looks like on top of your data. Now, it says describe the strength and direction. Well, this is strong negative correlation. So we'll move that up by our data here. You can see that strong negative correlation right there. Then use the model to predict weekly cereal sales if the prices drop to $2 or raise to $4. So what we want to do, we want to find f of 2 and f of 4. So we're going to put that in here. Second trace value at 2 be 42,904.64. That's going to be about 42,905 boxes. And then again, if X is 4, be 12,186 boxes. 0.78, or about 12,187 boxes of cereal. That's how many boxes the store brand throughout their entire chain will expect to sell if they raise their price to $4 or lower their price to $2 a box. Hence why you always see the sale at our local supermarkets. If they have a surplus that's when they sell it first, put it on sale. If they don't have a lot, that's when you don't see the sale.